And today we have Ahmad from Heriot University. He's towards the end of his PhD, and he's going to present his study on subsurface hydrogen and the role of microbial communications. It is even though his work is focused on hydrogen storage, but it's very also relevant to hydrogen generation, because whatever we want to generate subsurface, we need to make sure microbes won't eat it. Just before starting a presentation, I just want to mention this part that now the conference this year for GHyGeNet will be online only, so everyone can attend. And there won't be an in-person one. It will be just online, and it will be on 4th and 5th of December. I've already shared the abstract submission link. So if you want to present there, please submit your abstract by 10th of November. Last year we only had the invitation only speakers, but this year I thought maybe it's good to give everyone a chance if they want to present. Already some people have submitted their presentation. Like, please, if you are considering to submit, please go ahead and submit. Thank you for joining today, and thank you, Ahmad, for accepting our invitation. Please go ahead and start your presentation. I'll mute our side.
Okay, thank you very much, Ali. I suppose all of you can hear me. Hello, everyone. Good morning. Thanks for being here. Thank you, Ali, for providing this opportunity that I can present my PhD study. The topic of my PhD is numerical study of microbial and geochemical reactions during underground hydrogen storage. And let me introduce my supervisory team. They are Dr. Saeed Khambari, Dr. Gang Wang, and Professor Eric McKay. Here is my presentation outline. At the beginning, I will explain the problem definition and the research goals. After that, I will talk about the first part of my PhD, which is about building a conceptual model of underground subsurface hydrogen systems, which is about building a bio-geochemical model, a batch model. After that, the second part of my PhD is about integrating that batch model, that bio-geochemical batch model, with fluid flow in porous media or transport equations. And after that, I will provide some examples, use of the model, and finally, the conclusions and summaries. So let's start with the problem definition. This schematic simply shows the role of underground hydrogen storage in the energy transition scheme. And the idea is that we can generate hydrogen from the surplus energy which is produced from renewables, wind, waves, solar. We can generate hydrogen, and during the surplus, we can store it in a depleted reservoir, for example, a depleted gas reservoir. And during the energy shortage, the supply shortage, we can back produce this hydrogen and give it to the grid to balance the mismatch between green energy production and the demand. However, introduction of hydrogen into subsurface systems may induce some geochemical instabilities and also some microbial reactions that may those microbes can consume hydrogen, and as a result, it will impact hydrogen purity after back production. You may have some contamination in your hydrogen stream, and also it impacts hydrogen recovery. So this study aims to first addressing the biogeochemical knowledge gap in this context, and then developing a multi-physic reactive transport model tool for underground hydrogen storage. So let's go to the first part, which is a biogeochemical model. In this section, I'm going to explain, to show you a conceptual model about hydrogen storage. This schematic shows a conceptual model of hydrogen systems, assuming we have a depleted gas reservoir, and in the system, we may have three phases: a gas phase, a water phase, and a rock phase. So in the rock phase, we may have some minerals, and these minerals are in equilibrium with the water phase. we may have calcite, we may have dolomite, we may have anhydrite, and any other minerals we can add to this system. In the water phase, we will have speciation reactions. For example, here I put carbonate system speciation reactions, or here shows the sulfite system speciation reaction. And in the gas phase, we may have CO2. It may be used as a quotient gas, or maybe it is present in the reservoir initially, as well as methane and hydrogen. So we are injecting hydrogen. It is assumed that this system in equilibrium. And in the context of hydrogen storage, there are three main microbial reactions, which are methanogenesis, acetogenesis, and sulfate reduction. In methanogenesis, you can see that hydrogen is reacting with bicarbonate and generating methane. In acetogenesis, again, another microbial path, hydrogen is reacting with bicarbonate and generating acetate. In sulfate reduction, hydrogen is reacting with sulfate and producing sulfite, and H2S can be a byproduct of this phenomenon. So based on this conceptual model, these reactions, this interaction between phases, I have built a model in Frixy software. Frixy is a geochemical software, and it is assumed that all geochemical reactions are in equilibrium. I mean, rock dissolution and precipitation, they are in equilibrium. These speciation reactions, they are in equilibrium. Gas dissolution in the water phase and vice versa, gas exsolution in the gas phase, they are in equilibrium. And these microbial reactions, methanogenesis, acetogenesis, and sulfate reduction, they are controlled by a rate model. And you can find more details about this study in this paper. So let's go to microbial reactions. In this table, you can see that I have put three microbial reactions: methanogenesis, acetogenesis, and sulfate reduction. I always say that my background is reservoir engineering. When I started my PhD, I knew nothing about microbiology, and I started from zero in microbiology. And the first thing that I found about microbial reactions was that each microbial metabolism contains two separate reactions, a catabolic reaction and an anabolic reaction. We usually know the catabolic reaction path. For example, another notation of methanogenesis is reacting CO2 with hydrogen. If you do some math, you can convert it to that reaction. We always aware of this reaction, but in the anabolic reaction, it's another path of that microbial metabolism. In this reaction, microbes reproduce themselves by the energy that is provided by the catabolic reaction. In each microbial metabolism, the catabolic reaction releases energy, and anabolic reaction consumes that energy. It's the story behind each microbial reaction. So keep in mind these reactions. By these assumptions, we built our microbial systems. We assume that each metabolism includes two reactions, a catabolic reaction and an anabolic reaction. The catabolic reaction shows the hydrogen consumption, and the anabolic reaction shows the biomass growth or decay. We added a modification to the rate model. I will explain later in the next slide. We assume that the rate of reaction is pH, temperature, and salinity dependent. It means that microbes cannot survive in any range of pH, temperature, or salinity. Another assumption is that we assume that only catabolic reaction can limit microbial growth. We assume that the elements that are needed for microbial growth are always present, and only catabolic reaction can limit microbial growth. It means that we assume that there is unlimited access to nutrition. There is no limit for anabolic reaction. And we use some numbers to build the initial condition of our system. For example, for microbial reactions, we need some microbes present in the system. They cannot grow from zero. For example, we put this number as the initial condition of our system. We assume that in each milliliter of water, there are this number of cells of microbe, and they can grow to this maximum value. And yes, it is the story about microbial reactions. And the rate model that we have used for microbial reactions is dual monod rate model. In dual monod rate model, rate of reaction, rate of hydrogen consumption is a function of a specific growth rate, which is unique for each metabolism. It has a number for methanogenesis, acetogenesis, or sulfate reduction. Y is the yield coefficient. Yield coefficient is a kind of stoichiometric factor which relates catabolic reaction with anabolic reaction. We have Y here. And the rate of reaction is function of concentration. D is for electron donor, A is for electron acceptor. In the context of hydrogen storage and microbial reaction for hydrogen, electron donor always is hydrogen, and electron acceptor, for example, in methanogenesis, is bicarbonate, or in sulfate reduction, it is sulfate. And last but not the least, the amount of microbe, which you can see that the rate of reaction is dependent to the amount of microbe. It means more microbe, more reactions. And another term for anabolic reaction, which shows the biomass density or biomass population, which is the summation of growth rates. It is growth rate minus death rate. We calculate the growth rate using the monod model, and there is a term named B here, which is the decay coefficient. It says that always a portion of those microbes will die. So when the growth rate is higher than the death rate, we will have microbial growth, and the population increases. This table shows each unit, each parameter, which its unit. For the pH, temperature, and salinity dependency, we correct the rate of reaction here by defining some simple functions that generates a factor between 0 and 1. For example, for pH, this function generates a factor between 0 and 1, and this factor at the optimal condition means the best situation for microbes. This factor is 1, and when the condition deviates from the optimal condition, this factor deviates from 1 and converges to 0. For example, this chart shows the correction factor for methanogenesis for pH. The optimal condition is something around the 7.7, and when it deviates from the optimal condition, it starts to decline. And the boundaries for methanogenesis is around it's between around 4 and 10, and when pH reaches to those numbers, the reaction will be stopped. In terms of geochemical reactions, so I told that we used the FRIXI, and in all the FRIXI database is included. All the reactions are included in the system. The main reactions in this context are carbonate system. I showed you the reactions in the conceptual model, a speciation reaction for carbonate system, for sulfite system, hydroxide mineral. It's likely for hydroxide minerals to precipitate. I will explain. And another effect is for geochemical reaction is temperature effect, which internally FRIXI calculates that. And this table shows some important geochemical reactions in this context. So after developing this model based on these assumptions, we performed a simple batch simulation study to understand how such a system works. I mean, defining a system with the 3 microbial reactions, methanogenesis, acetogenesis, and sulfate reduction, and we will have some geochemical reactions. So we can define some mineralogical setups. I mean, some system with different geochemical properties. For example, assume you have a reservoir with calcite, or you have a reservoir with quartz, or you have a reservoir with dolomite rock. So we defined the system using the North Sea water as the initial brine. We tested the 3 rock mineralogy: a pure calcite system, a pure dolomite system, and a pure quartz system. With this given condition, and we run the model, and we observed different pH behavior in each system. In a calcite system, pH reaches to around 10. If you remember, it is one of the boundaries for methanogenesis. In a quartz system, it has a stable behavior. Or in dolomite system, we are observing a strange behavior, increasing, then decreasing. Or if you are familiar with North Sea seawater brine chemistry, the North Sea water has a high amount of sulfate, and in SRB or sulfate reduction reaction, hydrogen will react with sulfate and generate HS-, and that HS- will contribute to production of H2S in the system. We will have some H2S in the system. Again, we can see a different behavior. In a quartz system, a stable behavior. In a dolomite system, we can see that it is completely following the pH trend. And again, in a calcite system, again, we can see that H2S concentration is following the pH trend. So the question is that how microbial reactions leads to these geochemical reactions and this geochemical different behavior. We can explain it in a way that microbial reactions are disrupting the equilibrium. If you remember, for example, methanogenesis reaction, hydrogen is reacting with bicarbonate, and the concentration of bicarbonate is decreasing, and we will have equilibrium disruption. And this equilibrium disruption leads to geochemical reactions. And again, this loop happens. Somehow, a positive feedback loop is created. So I can explain the methanogenesis reaction here. In methanogenesis reaction, if you look at to the reactants, because of this reaction, the concentration of bicarbonate and hydrogen is decreasing because of the reaction. So as a result, if you remember from high school chemistry, when the concentration of hydrogen is decreasing, the system behaves in a way to resist this change. So more hydrogen will dissolve in the system, in the water. On the other hand, for bicarbonate, the concentration of bicarbonate is decreasing. The system behaves in a way to resist this change. So in a system that we have dolomite start to dissolve to compensate that reduction in bicarbonate. At the same time, dolomite, if you remember the chemical formula of dolomite, it is CaMgCO3 twice. Dissolution of dolomite will increase the calcium ion and magnesium ion concentration in the water phase, and as a result, we will have calcite and borusite. Borusite is MgOH precipitation in the system, and the final result will be the pH will be buffered. If you remember the pH behavior for dolomite system, pH will be buffered, and we will have a continuous generation of bicarbonate, which leads to more methanogenesis. We performed another study using that conceptual model with different rate model for microbial reactions. There is another rate model named single monode. I showed you dual monode. The modified single monode and modified dual monode. It's the rate model with that pH modification I showed you, pH temperature modification I showed you. Our model is working with this rate model, but we wanted to do a sensitivity analysis on rate of reaction on rate model. And Arrhenius rate model is the rate model which is widely used in reservoir simulators. For in reservoir simulator, there are two famous rate models: TST rate model and Arrhenius rate model. TST is suitable for mineral dissolution precipitation, and Arrhenius rate expression is suitable for reactions in the H2S phase. So we wanted to see whether Arrhenius rate model, which is used in a reservoir simulator, is able to reflect this behavior or not. So we assume that we assume pH as a matching parameter for Arrhenius rate expression, and we matched the Arrhenius model with the pH. But if you look at the rate of reaction, this chart, you can see that the black dash line is the black dash line is not able to predict the initial behavior of the system. The dual monode, single monode, and modified rate models are predicting the rate of reaction starting from something near to zero, starting from zero somehow, and they are reflecting the microbial growth. But the Arrhenius model is not able to reflect the growth part, and somehow it is overestimating the rate of reaction. Other charts show the amount of hydrogen in the gas phase and methane production from methanogenesis, and dolomite dissolution and calcite precipitation. So let's go to the next part. Actually, before that, the conclusion of this part is that we found that from this study, there is a great interplay between microbial and geochemical reactions. And it's important to consider mineralogical setup of each reservoir for any hydrogen storage project. So let's go to the next part, which is about integrating the bio-geo model with transport in porous media. So why we did that? The reason we did that is that we wanted to see the dynamic of underground hydrogen storage. I mean, from injection, fluid flow through porous media, plume migration, and back production of the plume. To see the dynamic of UHS, so we need to have a reactive transport model. And by using this algorithm, we coupled the bio-geo model that I showed you based on that conceptual model with an open source reservoir simulator, which is a MATLAB reservoir simulation toolbox. We coupled that model in Frixie with a compositional simulator in MRSC, and we named it UGFACT, underground gas flow simulation coupled with reactions. The idea is that the way of coupling is somehow one-way coupling. Those who are familiar with the behind the scene of reservoir engineering, they are familiar with one-way coupling. But in details, the idea is that we solve the fluid flow implicitly using our reservoir simulator and calculating the variables in the next time step. I mean pressure, saturation, and composition. But before going to the next time step, we took all variables, all the amount of, for example, each composition of each component, pressure, saturation, volumes, everything. We take it to our bio-geo model and solve the reactions and update the variables. I mean the composition, pressure, and saturations. And then we use these updated variables as the initial condition for the next time step. It's somehow solving this solving the problem by implicit flow and explicit reactions. This flowchart shows the details of coupling. We initialize the system by defining the system by giving pressure, temperature, global mole fraction, the injection scenario, everything, and the geochemical condition, concentrations, pH, mineralogy, solving fluid flow, calculating all variables, and then take them to the bio-geo model, update them, and then go to the next time step. There are some challenges. The first one is the importance of time step selection, because it's something like implicit solution in reservoir engineering, implicit pressure, explicit saturation. The use of we cannot use large time steps for simulations. We should be careful about that. Another challenge is that we have two different thermodynamic engines. We have one thermodynamic solution in a reservoir simulator, and we have another thermodynamic engine in our bio-geo model. And the point is that the input and output here, they must be consistent in terms of thermodynamic. And to overcome this problem, before taking all variables after the bio-geo model, we perform a flash calculation. The model performs a flash calculation using the MRST thermodynamic engine to make it consistent in terms of thermodynamic for the fluid flow. And another challenge is runtime. When we want to do simulation in large models, because we are performing the batch calculation for each cell separately, the runtime would be extensive. So we developed this reactive transport model based on this framework I showed you. And before doing anything, we benchmarked this reactive transport model. So we defined a system, a simple system, a two-phase system with water and gas, and three components: water, CO2, and methane. Using a Penn-Robinson equation of state, we defined a simple 1D reservoir with this given dimensions, with 50 cells in X direction, assuming porosity 20% and permeability of 100 millidarcy. And this initial condition, assuming there is the saturation of water is 94% in our system, around 94%. And we have a 1D system. We are going to inject CO2. I'm sorry. We are going to inject CO2 from the left side of the reservoir. I'm sorry. From the left side of the reservoir, and we have put a producer just to keep the pressure constant, the pressure gradient in the reservoir. We put a producer at the initial reservoir pressure here. We are going to inject CO2 in a reservoir which is saturated with 94% water and 6% methane. And the mineralogy here is calcite. We defined these simulations in three reservoir simulator. We defined this simulation in E300 using the gas-vat model, in GEM, including geochemistry, because GEM is able to predict and calculate mineral dissolution and precipitation. If you are familiar with geochemistry, and we have a calcite system, a carbonate system here, and we are going to inject CO2. We expect some rock dissolution because CO2 will make the brine acidic, and some rocks will be dissolved in the water phase. And the last one, we defined this injection scenario in our model, assuming we have no microbial reactions. When we assume we have no microbial reactions, our model and GEM behave in a similar way, and we expect to have a match between our model and GEM in terms of geochemistry behavior. Here are the results. There are 4 snapshots of gas saturation in different time. We can see that there is a good match between GEM, E300, and our model in terms of predicting gas front, in terms of fluid flow behavior, and in the geochemistry behavior, again we can see that there is a good match between our model and GEM in terms of pH, the amount of calcite dissolution, and the amount of calcium concentration in the water phase. So this benchmark showed us that we can trust on our model, and after that, so we can do some studies using that model. So in this section, let me check the time. I'm going to show you some examples of using of my model. So we performed an underground hydrogen storage in a 1D system. In this condition, again, assuming a two-phase system, a water-gas system, in the model, it is assumed that we can define 6 components. These components: water, hydrogen, CO2, methane, H2S, and nitrogen. The injection scenario is that I'm sorry. 50 days of hydrogen injection, 150 days of shut-in, and 50 days of back production. I'm really sorry. And it is the injection scenario. In 3 mineralogy, we found this mineralogical data from literature: Bentheimer sandstone, Berea sandstone, and gray Berea sandstone. And in 3 microbial conditions: a no microbial condition, moderate rate, and the high rate. This table shows the initial condition for geochemical, for mineralogy and brine composition. And these profiles show the mole fraction of hydrogen in the gas phase in each reservoir. You can see that the red line shows the high rate condition. The red line is deviating from the no reaction condition, and during storage we are losing some hydrogen in our system. In the Bentheimer sandstone and Berea, they have a similar behavior, but you can see that in gray Berea sandstone, the amount of loss is limited. It's not like Berea. Thank you. It's not like that. These charts show the pH behavior in these 3 reservoirs, and you can see that in gray Berea sandstone, pH is rising and reaching to around 10, which, if you remember, it is the boundaries of methanogenesis. But in the first 2 reservoirs, it is buffered in a desirable range for microbes. And this is why we will have more hydrogen loss in these 2 reservoirs. And this chart shows the amount of hydrogen loss per each grid block after the storage in the moderate rate condition and in the high rate condition, and the share of each metabolism. The reason is that sulfate reduction is limited in this system. There is no sulfate source in the system. The only sulfate source in the system is the initially dissolved sulfate in the system. But in this simulation, you can add a few percentage of the anhydrate, and you can see that the share of sulfate reduction will be increased because anhydrate can dissolve in water and provide sulfate for this microbial reaction. Another study that we performed was about investigating the role of heterogeneity in reservoir and its impact on microbial reaction dynamic. So we built a 2D aerial model, and we're going to inject from the left side by defining a horizontal well in the left side, a system with 194 cells in X direction and 40 cells in Y direction. The initial condition, water saturation is 25%, and we have 75% methane. And the reservoir mineralogy is 98% quartz, 1% calcite, and 1% dolomite, something near to Berea sandstone. Assuming only we have methanogenesis and using 2 different rate of reaction, a high reaction rate and a moderate reaction rate. And we perform this simulation in 2 reservoir systems, a homogeneous system, I mean the permeability is constant, and in heterogeneous reservoir, which we have a distribution of permeability in the reservoir. 100 days of injection, 100 days of shut-in, and 100 days of pack production. This profile shows the permeability field, which is distributed along the reservoir, and we are going to inject from the left side of the reservoir. Because of the runtime problem, it is the original permeability field. I upscaled it using some simple averaging method. And so let's see the results.
কিরে
হ্যালো
কি
আমার প্রভু এসবিআই তে যাবো
যা মুখের মধ্যে
No
আমি
problem.
এখন এই জন্য
So this profile shows the hydrogen mole fraction in the gas phase. The first, this one is in the heterogeneous case. The second one is in the homogeneous case, and the third one is the difference between heterogeneous case and homogeneous case. So This profile tells us that there is a difference between heterogeneous and homogeneous case, but we cannot find out how much is the difference in terms of hydrogen loss. So let's go to the rate of reaction profile in the system during injection, shut-in, and back production. The first one shows in the heterogeneous case rate of methanogenesis reaction in millimoles per kilogram of water, and you can see that in heterogeneous case the difference part for heterogeneous is higher than the homogeneous case. It means in heterogeneous case, we will have more reaction and we will have more hydrogen loss in the system. Or this profile shows the pH propagation in the reservoir. We can see that there is more affected area because of reactions in heterogeneous case compared to homogeneous case. And this profile shows the amount of rock dolomite dissolution, because dolomite here is providing bicarbonate for methanogenesis. Again, we can see that in heterogeneous case, it is confirming the rate of reaction profile, the pH profile. There is more, in total, there is more dolomite dissolution in the heterogeneous case. And the reason is that heterogeneity will disperse the plume in the reservoir, and the hydrogen plume will touch more area, more microbes, and it is more available to present microbes in the reservoir, and we will have more reactions. It shows that the degree of heterogeneity and including heterogeneity in our systems for UHS scenarios are important. And last but not the least, the last study that I'm working on that is performing a multi-cycle storage in a certain reservoir. Actually, a couple of months ago, I found a paper from Ali Akbar, which he has reported the mineralogy of raw field in the UK, which is used for gas storage. And so when I found it, I got so happy, because one of the main inputs of my model is the mineralogy. And for the raw field from 5-6 cores, I think during the highest torpor project, they have measured the mineralogy of a couple of cores, and they have reported the mineralogy of each core. So based on that mineralogy, I performed a multi-cycle storage in a synthetic reservoir. I defined this permeability and porosity field with this correlation length in x direction 100 meter, in z direction 50 meter. A very simple model, and I ran the model for 20 cycles of storage, annual storage, 5 months of injection, 2 months of shut-in, and 5 months of back production. Here are the results in terms of hydrogen purity, average purity versus cycles. There are two lines. A red line shows the case, assuming we have no microbial reactions, and the blue line shows the case that we have some microbial reactions in the system. The bar chart show the difference between the no reaction case and with reaction case. We can see that at the earliest stages, we may lose some hydrogen purity in the first 4 or 5 cycles. But in the late cycles, this difference will decrease, and the case with microbial reactions converts to the case that we have no microbial reactions, which shows that after some cycles in the early time, there is no concern of microbial reactions in the late cycles. The same thing for hydrogen recovery. We can see that the difference between the case with reaction and no reaction, it is converging in the late cycles. Again, the bar chart shows the difference. Initially, it is increasing, and then it starts to decrease the difference. So, in summary, we found that there is a great interplay between microbial and geochemical reactions. The simulation showed us the importance of site screening for underground hydrogen storage. Dolomite reservoirs may have some operational risks, but the result showed that the risks can disappear in the late cycles. we found that there is a limitation of current rate models in reservoir simulators. I showed you the Arrhenius rate model for modeling microbial hydrogen consumption. So in this study, we integrated FRIXY with MRSC, and we developed a model which is named UGFACT. It is available online. All the codes are released. You can find it in my GitHub profile. We found the importance of the impact of mineralogy on UHS projects. We found that heterogeneity can increase hydrogen loss. And another important finding is that after some cycles, we found that UHS performance converges to the case with no reaction. And here are the references that they are the outcome of this PhD. And there will be a couple of papers in the future, I hope. Thank you for your listening, and I'm here for your questions.
Thank you, Ahmad. It was an excellent presentation. I think I'll get the questions from online people first this time. So I see Nargisa has a question. Yes, please go ahead, ask. Nargisa Kabaj, please ask the question.
Hear me?
Can you speak louder?
Can you hear me?
Yes.
Thank you very much for your presentation. I have just a question concerning the relative permeability. Did you take the hysteresis in your simulation? And do you think that it will have an impact, especially about the cycles? At the end, you see no difference. So, is the hysteresis will impact this?
Yeah, I think I got your question. You asked what relative permeability hysteresis effects. In my model, no, the relative permeability hysteresis is not included. But I think relative permeability hysteresis will increase hydrogen loss due to microbial reactions, because when you add hysteresis into your simulation, you will have an immobile hydrogen phase in your system. You cannot move that because of hysteresis, and they will trap there, and they will be available to microbes if they they exist and they are present there. And I guess adding hysteresis will increase the amount of hydrogen loss in terms of microbial loss, because it will be trapped there, and there is time for microbes to consume them.
Thank you. So FJ, Abuna?
Yeah, good morning. Thank you so much, Ahmed, for your wonderful presentation and also very interesting area too. I have two questions. I think you answered them probably. Let me ask them together, then you may be able to answer them one after the other. The first question is, what are the possible impurity before and after withdrawal from underground storage? And then the second question border on econs. What are the percentage loss of hydrogen after withdrawal?
Thanks for your question. In terms of impurities, in methanogenesis reaction, we are in this metabolism, hydrogen is reacting with CO2 or bicarbonate, and methane is the byproduct. Methane can be an impurity, but most of hydrogen storage projects are defined to be performed in depleted gas reservoirs. And in depleted gas reservoirs, always there are a high amount of methane in the system. So if even you don't have any microbial reactions in your system, you will have some impurities in terms of, because of gas mixing. Hydrogen will mix with methane, and during back production, you may produce some methane with hydrogen. If methanogenesis exists in the reservoir, you will have more methane in your producing gas stream as an impurity. So there may be some other gases in the system, methane, ethane, propane, any other host components in the reservoir. And another one is H2S. If sulfate reduction is an active metabolism in the system, you may have some H2S. Our simulations showed it can reach to several hundreds ppm of H2S in the producing gas stream if there is a source of anhydrate and also microbes in the system. In terms of the amount of hydrogen loss, it totally depends to the rate of reaction. We couldn't find a clear data in terms of microbial reactions. I think Marcus is here from RAG Austria. I read one of their papers. Actually, they have reported a rate of reaction in one of their papers, and they have measured it in the lab. And the rate of reaction that we are using in our simulations, it is something near to that rate. And we found that it can be in each cycle a few percentage, for example, 4 or 5% due to microbial reaction. You may have a hydrogen loss. But I'm sure Marcus can answer this question much more clear than me.
I'm not sure I can. Good morning. Thank you for your presentation, Ahmad. Thank you. Well, I mean, actually, yes, we did measure the reaction rates in the laboratory as well as we measured them in the field. And you saw the clear difference between the laboratory where we had high reaction rates naturally due to the smaller space. So the communication of gas and microbes is much, much better than you have it in the reservoir where you have a porous system where the communication is not that good. Therefore, the rate of reaction decreases by a factor of 100. So it's much, much slower than you see it in the reservoir. And what is more interesting even is if you inject pure hydrogen, then you basically see no reaction rate. I mean, that's at least our current state for both laboratory experiments as well as the experiments that we had in the field, because there is nothing to react with. So we don't see, and that would actually be my question to you, Ahmad. You see a dissolution of carbonates, so basically dolomite, but also maybe calcite, and that would be my question. You see the rate of reaction decreases in your model at the end of your 20 or whatever cycles. So what limitation do the microbes actually run into that this rate of reaction does decrease? Because if you just think about the bulk volume of carbonates that are available, they would still be available. So it is some kinetic thing, I guess. And the second question that I would have is, what is your way forward? Because I'm really curious if you're planning to verify the model that you generated, which is really cool. So I was impressed with some real world data.
Thank you, Marcus, for your question. Let me share my screen.
And if you answered the question already, I'm sorry, I was late 10 minutes. That's my fault.
No. So you asked your first question about this chart, yeah?
Exactly, yes.
In the model, the reason is that the case with reaction is converging to the case with no reaction is dolomite depletion. I think the amount of dolomite content in this simulation is something like 1%. It's not the whole reservoir.
You said 1% of the Berea sandstone, but
yeah,
if you're calculating, I mean, I think you talked about the rough field. No, that isn't the rough field. That's just the Berea sandstone,
it's
generic
rough
one.
field. It's rough field. It's rough field, and it's about, I think, 1 or 2% dolomite in the simulation. And the reason is that the model assumes that any amount of dolomite that you define in your system is available to react. So you can modify it. For example, if your reservoir has 2%, but in reality all of that dolomite is not available to react. But in this simulation, all of them are available to react. And the reason that they are converging to the case with no reaction is dolomite depletion.
Okay, that makes sense.
We have some questions on the text, on the chat part as well. Maybe if you can give a very short answer to them, so because I see some more hands are up as well. So Shankar asked, how did you determine the optimum pH range? Was it based on literature review or simulation? If it was based on simulation, what parameters did you consider when selecting the pH range?
Sure. Just to finalize my answer to Marcus. Marcus said, "Do you have any plan to verify?" Yeah, I'm open. I'm open to collaborate with field data. I'm hungry for field data. We can have some collaborations, and I will send you a message about that.
Yes,
Maybe
please. I would ask you for that, please.
Okay, thank you.
Thank you so much, Ahmad.
You're welcome. In terms of pH range, we found it in literature. I saw here Ike Tyson. We used her paper. They have published an Excel file with around 500 metabolisms for methanogenesis, acetogenesis, and sulfate reduction. And for example, for methanogenesis, we averaged them. They have reported a minimum pH, maximum pH, and optimal condition, and we averaged them. We averaged the optimal pH, maximum pH, and the minimum pH. Because for each metabolism, we assume that there is only one metabolism. In reality, for example, methanogenesis, there are many microbes. I'm not microbiologist. I think Ike maybe can explain it better. There are many microbes that can do that reaction. But in the modeling, we assume that there is only one microbe that is responsible for that reaction, and we took the limits from literature. The second one, yes, it was based on literature. So it was about pH. Next question.
Yeah, we have another question from Christopher. You assumed no limitation by nutrient availability, but this can be as big a limit to microbe growth as energy, especially for elements such as phosphorus. We include these in radioactive waste-related microbe modeling. Do you plan to include nutrients in any future calculations?
It's a good question. There are some methods to include the nutrients effect on anabolic reaction. And if you remember the dual monotrate model, there was a term for electron acceptor, there was a term for electron donor. I have seen in some sources, I've read the UTChem. UTChem is an in-house reservoir simulator for University of Texas and Austin, I think. In their documentation, they have used another term, something similar to electron donor term, electron acceptor term, another term for nutrients. And when the concentration of nutrients becomes zero, the rate of reaction will become zero as well. In terms of any future work, I'm wrapping up my PhD, and I guess I don't have time to do that. I've started writing my thesis, and at the same time writing some papers. And maybe next students, next generations, the code, the model completely is available online in GitHub, and anyone can access to the model and add any modification to that.
He also asked, did you include a rate decrease as the model moved towards the maximum pH?
Did you include a rate decrease? The way that I understand this question is that in the model, we have a function for pH dependency. And it's a correction factor, and it is calculated in each time step. In each time step, we will have a certain pH because of the previous calculations. For the next time step, we have a pH from the previous calculations, and based on that pH and the given maximum, optimal, and minimum pH, we calculate a correction factor for pH. And somehow it is accumulating based on the previous condition. So if pH is, for example, rising and reaching to 10, that correction factor is also reducing from 1 to 0. And eventually you can see that that impact is applied to the rate of reaction.
Maybe we also get the last question from Linkping.
Yes. I will put.
Yeah. Thank you, Ali, and thank you, Mr. Ahmad. Very interesting presentation. I have a similar question, or more like a comment, as Marcus, because we also I'm from Australia, CSIRO, and we are doing some geochemical experiments. And what we observed so far is like under typical reservoir temperature pressure conditions, hydrogen seems like doesn't really react with carbonate minerals like calcite, dolomite, as you talked in your presentation. So, because one of your slides show the variation of pH, for example, of calcite, it would increase. For dolomite, it would slightly decrease after reacting with hydrogen. I'm also using frequency to do this geochemical modeling stuff. So I'm just curious about, have you ever sort of modified the database you used to match the some observed experiment results? I mean, have you calibrated your model from the field data or experiment data? Thanks.
Thanks for your question. Just a quick question: are you performing only geochemical reactions, or is there any microbe in your experiments?
No, just pure geochemical.
Yes, the point is that if you do pure geochemical reactions, you will see no effect, no change. Hydrogen has no reaction in terms of geochemical reactions with rock. I think one of the main outputs of highest to poor project in the University of Edinburgh, which Ali Akbar was involved, was that they did a lot of experiments exposing hydrogen to some minerals, and they observed absolutely nothing, almost nothing. But the point is that when in the modeling part, when you add those microbial reactions, you need to add some microbes in your system. You add some microbial reactions.
Just make me clear. So in your simulation for the geochemical modeling part, no microbial reaction. Did you observe any interaction between carbonate mineral and hydrogen?
You said you are using Frixie. And in Frixie, it depends what kind of hydrogen in Frixie you are using. There is a reactive hydrogen in Frixie, and actually the methanogenesis reaction in the Frixie world, it is known as reduction of carbonate. It is defined in the database, and the K value is very high. If you perform a simple experiment in Frixie, define hydrogen and CO2 in the gas phase, and run the model, at the final stage you will have no hydrogen. All of your hydrogen will convert to methane.
Okay, we are running a bit over time. Maybe we cut this part so we finish on time. And just if it's okay, I would ask you maybe email or send a comment, because I want to get one last question from you. We are already over 11.
Thank you. Thank you very much.
This room. Probably send an email to Jake. Is there any final question from here?
Ali, let me put the link of my model in the chat.
Yeah, fantastic work, great presentation. I was intrigued, you mentioned your time step, that you had an issue with large time steps coming from the reservoir engineering culture, and you had a 1D model, 50 cells, I think. What was your time step, and did you have any issues around the model converging? Like, how long did it take to run, and was it tricky to get it to converge?
For example, just to give you an idea, for example, for doing the last simulation I showed you, let me share. The last simulation I showed you, the DT we selected was 5 days, and the injection rate. I think I don't have access to it, but it cannot be more than a couple of days in terms of time steps. And if you increase the time steps, you will have the overestimate of geochemical behavior.
Right. Last question from example. Okay, maybe you want to come back chat and finish.
Okay, so very quick on Ahmad. It's on lithology. You assessed 3 sandstones and first two behaved very similarly. The third one was different. Later on, you said it was almost pure quartz, 98%. So I suppose mineralogy affected it. Do you have any applicable results of lithology? Let's say that it could be used for site selection, for example.
Sorry, can you repeat your question?
The simple version.
What's the applicable result on lithology effect, which could be possibly used for site selection?
Yes, actually, it's one of the main output of this study and this PhD. The importance of site selection. We need mineralogical data, and also at the same time we need to collaborate with microbiologists because again I would say Ike is expert in this area. They do some microbiologists do some DNA test, something like that, and they measure the active culture in each reservoir. We need that site. We can use this model by inputting the, for example, there are several sites in the UK that they are candidate for hydrogen storage. We can take those mineralogical data, put beside the microbiological data, those RNA DNA tests, and we can use this model as a screening tool for hydrogen storage projects.
Final question.
Thank you, Ahmad Raza. I had a question on slide 23. You mentioned that the contribution of sulfate-reducing bacteria is limited. And my question is that by considering the high amount of sulfate in seawater of North Sea, how we cannot see any effect of SRBs?
In this simulation, the amount of initial sulfate, it's for Bentheimer sandstone. The initial amount of sulfate in the system is this amount, and there is no other, there is no any mineral that can provide that sulfate, and it's not North Sea water. It's less than North Sea water, and this
so
is
it's
the
a formation
reason.
brine, though. Then it's a formation brine concentration.
Yeah. It's a formation brine. Yeah.
Yeah. Okay. Good. Thank you.
Thank you, Ahmad, for your presentation today. Sorry, everyone, it ran a little bit over time. Thank you for joining today. And thank you for accepting our invitation to the excellent presentation, and thank you for answering all the questions nicely. I hope you have a nice day and a very successful defense for your PhD. Thanks.
Thank you very much. Anyone, if you have any question, I put my email. I think you have my email from Ali Akbar's email. You can reach out, and I try my best to answer your question. Thank you very much, Ali.
Thank you very much. Have a nice day.
Bye.
Thank you. Bye.
Yeah.